Welcome everyone. In this video, we are diving into a real world challenge, enabling communication between two ECS services running in separate AWS accounts. Here is the problem. Service A in account A needs to communicate with service B in account B. Both services run as ECS tasks, meaning their private IPs change frequently as tasks are replaced. Since direct IP based communication is not reliable, we need a hostname based approach with a middleman resolving the hostname to the correct ECS task's private IP. So let's explore various solutions. Number one, AWS App Mesh could have been an option, but AWS is decommissioning it by September 2026, so we can't use it. ECS Service Connect is number two. It works well, but only within the same AWS account. So it is not a viable solution for cross-account communication. So what are the other alternatives? There are multiple ways to solve this, and in this video we will explore a practical solution called Centralized DNS Management through a hands-on demo. Let's get started. To implement and demonstrate this solution, we will be working with three AWS accounts. Hub account where we will set up a centralized DNS, Spoke account A where service A is running, Spoke account B where service B is running. Service A in account A will communicate with service B in account B through the centralized DNS in the hub account. This setup ensures reliable service discovery across accounts without relying on changing private IPs. Let's dive into the implementation and see how this works in action. You need to clone this repo. I have already cloned this. So I have three accounts, account 1, account 2 and account 3. So I have set the profiles for all the three accounts. Account A1 will be the hub account. Account A2 will be the spoke account A. Account A3 will be the spoke account B. So this is my make file. You can deploy the entire infrastructure through a single command called make apply. But let me deploy the resources incrementally step by step. Let me navigate to the Terraform folder and run Terraform in it. It is done. Let me go to the root folder again and run make deploy ram shares. Okay, this is completed. So that command will create resources in account A1, A2 and A3. Now we are in A1 region Mumbai. So I'm in RAM. So the resource shares shared by account A1 with account A2 and A3 is this example share. It is shared with the other two accounts. I'm going to account A2. It is shared with account A2 and this is account A3. So in this step we have created a RAM resource share in hub account and a RAM resource share acceptor in spoke accounts A and B. Now we have to create the foundational resources in hub account. This is done. So that created a VPC called DNS VPC in account A1, that is the hub account. It also created two private subnets called private subnet 1 and private subnet 2. So let's check the route table, no internet gateway, making it a private subnet. And a security group called allow all traffic has also been created. So it should have been named something else. It is not allowing all traffic, it is allowing only the DNS traffic. And this is the outbound rule. So in this step we have created a VPC in the hub account, two private subnets inside that VPC, a security group. AWS reserves an IP address for the DNS server. This is the base of the VPC network range plus 2. For example, if the CIDR range is 10.0.0.0/24, then the third IP, that is 10.0.0.2, will be the IP of the DNS server. So this is our DNS server IP. Let me explain what the network range plus 2 IP is used for. Imagine you have an EC2 instance inside this VPC and it needs to resolve a host name like, say, example.com. The DNS request is sent to the AWS DNS resolver, which is located at network range plus 2. This DNS resolver either resolves the request directly or forwards it to external DNS servers. That's why this IP plays a crucial role in internal and external name resolution within AWS. Let's create the resolver endpoints in the hub account. Okay, this is done. That created an outbound endpoint in the route 53 of account 1 and also an inbound endpoint. So it has created two random target IP addresses in two AZs for high availability. So we have created an outbound and inbound endpoints. Let's create the resolver rule in the hub account. Okay, this is done. That created a rule called example local forward rule in the hub account. You can notice one thing here. So the outbound endpoint is mentioned here, which is ending with 499 DA, which is this outbound endpoint, but the inbound endpoint is not mentioned here. This means that when someone tries to use this rule, they will be redirected to the outbound endpoint directly. But what is the use of inbound endpoint here? The ultimate goal is from the source, the request should be redirected only to the inbound endpoint but via outbound endpoint. So outbound endpoint is mentioned here, and these target IP address, these two addresses are the target IP addresses of the inbound endpoint, not the outbound endpoint. So let's remember this 012 and 0221. Let's go to outbound endpoint and check the IPs. It's not those IPs. Let's go to inbound endpoint. Yeah, these two are the IPs which we saw in the rule. So this is the link between the rule and the outbound endpoint and the inbound endpoint. So we have created the rule in the hub account. Do you remember why we created the RAM resource share in the hub account? So we basically are going to create two main things in the hub account and we'll share those things with the spoke accounts. Number one, the rule, the resolver rule, and number two is the transit gateway, which we are going to create later. Now we have to share the resolver rule with the spoke accounts. It is completed. This is spoke account A and the resolver rule is shared. This is spoke account B. So in the last step, we shared the resolver rule with the spoke accounts A and B. As I mentioned earlier, service A in account A will communicate with service B in account B, but not the vice versa. Because of this, it is only necessary to share the resolver rule with account A, not account B. However, we accidentally shared the resolver rule with account B as well, which is not required. The solution will still work perfectly fine even if the resolver rule is not shared with account B. Now let's run the next command. Okay, it is done. In this command, even though we did not explicitly request a VPC creation, it was automatically created due to a dependency when we tried to link the shared rule with a VPC in account A. Here's what happened step by step. First, the VPC was created because it was required for the operation. Then the shared rule was linked to the newly created VPC. So we are in account A, spoke account A. It created a VPC called my VPC, the ID of which is ending with 93FE. Let's go to route 53 and then rules. This is our rule. And if we see, this rule is linked with the newly created VPC in spoke account A, which is ending with 93FE. So in this step, a VPC is created and that VPC is linked with the shared resolver rule. Let's create a transit gateway in the next step. So in this step, we need to create a transit gateway in the hub account and RAM share it with spoke accounts A and B. Here is why. Our centralized DNS will resolve the hostname of service B in account B to its private IP for service A in account A. But even after resolution, communication will fail because these services are in different accounts with no network connection between them. For service A to successfully communicate with service B, a network connection is required. This can be achieved either through VPC peering, which is not scalable for multiple accounts, or transit gateway, which is more scalable and flexible. We have chosen transit gateway for this setup. Once we create it in the hub account and share it with the spoke accounts via RAM, and later we create transit gateway attachments, then only the communication between the services be successful. It is done. This is the transit gateway created in the hub account, and the transit gateway is RAM shared with account A and account B. So we created a transit gateway in the hub account and RAM shared it with spoke accounts A and B. In the next step, we need to create a private DNS namespace using AWS Cloud Map in account A. When you create an AWS Service Discovery private DNS namespace, it automatically creates a private hosted zone. Similarly, when you create a public DNS namespace, it automatically creates a public hosted zone in Route 53. Since we are creating a private DNS namespace, AWS will automatically set up a private hosted zone for us. We are going to do this in both spoke accounts A and B. After creating the private hosted zone, we are going to link each private hosted zone with the VPC in the hub account. I'm running it for account A now. Let me run it for account B as well. The process of linking the hosted zone in the spoke accounts with the VPC in the hub account is called association. After associating the VPC with the hosted zone, we have to create an authorization for it. It is done. We are in account A. A namespace called account2 example local has been created. Let us also created a hosted zone with the same name, account2 example local. Similarly, in account B, a namespace called account3 example local has been created. which has created a hosted zone in the same name. Now I am in account A. If you see the details of the hosted zone, it is linked with two different VPCs. This 93FE is the VPC in account A, and this D07 is the VPC in the hub account. Similarly, these are the hosted zone details in account B. The 766 VPC is in account B, and D07 is the VPC in the hub account. So this is the association between the hosted zone and the VPC in the hub account. So in this step, in both the accounts, in both accounts A and B, I created a cloud map namespace which automatically created a private hosted zone, account 2 example local in account A and account 3 example local in account B, and we created an association between the private hosted zones and the VPC in the hub account. In the same step, we have also created the association authorization and a VPC in account B. Let me explain how authorization works here. Anyone with access to the VPC in the hub account will automatically have access to the private hosted zone in the spoke accounts. This poses a security risk, so in the next step we need to remove this association authorization to restrict unnecessary access. It is done. So in the next step we have deleted the authorization. In the next step we have to deploy the foundational resources in spoke account A. It is done. In this step we are configuring a public subnet by creating an internet gateway and attaching it to the subnet, creating a route table and associating it with the subnet, creating a transit gateway attachment in account A and linking it to the RAM shared transit gateway, setting up a security group that allows traffic on port 8080. We have also added a route for transit gateway. This subnet is public because we need to access service A in account A from the public internet. So this is what we have done. We have created a public subnet, internet gateway attaching it to the public subnet, a route table association, a security group which is allowing traffic on port 8080, a transit gateway attachment which is linked with the RAM shared transit gateway. So in the next step in account A, we have to create an ECR repository, build a Docker image and then publish it to the ECR repository. It is done. This is the ECR repository created and this is the image. So in this step, we have created the ECR repo in account A. In the next step, we need to deploy ECS service and ECS tasks in spoke account A. It is done. Before proceeding, I recommend watching my previous videos on AWS App Mesh and AWS ECS Service Connect, where I have covered all the essential resources needed to deploy ECS services and tasks in AWS. In those videos, I have explained about ECS task role and ECS task execution role, the required IAM policies for those roles, task definition, cluster setup, linking ECS service with service discovery, etc. Make sure to check them out for a deeper understanding. I'm I'm in account A. An ECS cluster is created. It has service A, and there is a task running under service A. This is the task definition. The security group is linked. A container called service A is running. This is the task role and this is the task execution role. Let's launch the public IP. Okay, the application is loaded. When I try to hit the get country button, I'll get an error because we are yet to set up the service B. So in this step, we have created the ECS service in account A. The private IP of this task is this 1.38. If you go to Route 53 hosted zone, an A record would be created with this name service A account to example local with this private IP. This A record is added automatically because we have linked our ECS service with the cloud map namespace. So that's what you are seeing here, service A account to example local. In the next step, we are going to create foundational resources in account B. Okay, this is done. I have created a public subnet in account B similar to the public subnet in account A. Ideally, the subnet in account B should have been private since service B is not meant to be accessed from the public internet. It only needs to be reachable privately from service A in account A. However, making it private would require either an AD gateway or multiple private links in account B. To keep things simple, I have created the subnet in account B as a public subnet even though it is not intended for public access. I have also created a transit gateway attachment in account B and then link that with the shared transit gateway. I'm not going to repeat all those things again. So in this step, we have created a public subnet, a security group which allows traffic on port 8080 because service B is also running on port 8080, a route table, a transit gateway attachment and linking that with the RAM share transit gateway, all those things. Let us quickly deploy the ECR repo for service B in account B. It is done. The ECR repo is created and the image is uploaded. In this tab, we have created the ECR repo in account B. Next, we need to deploy the ECS service in account B. It is done. The task is provisioning. Actually, it need not have public IP. When you try it, you can create this without public IP. Service A is going to communicate with this service B only through the private IP. And this IP will be resolved with the help of our centralized DNS. Okay, it is running now. Okay, anyway, we have created the public IP. So let's test the endpoint. Okay, it is giving us various country names. In this step, we have created the ECS service in account B. It has name service B account 3 example local. Okay, we have deployed all the resources. We have loaded service A in the browser. Let's see what will happen if I hit the get country button. So as soon as I hit this button, this home controller will get called, and this will make a call to service B account 3 example local colon 8080 slash country API. So when that button is hit, a DNS query is sent to the DNS server of the VPC in account A. This DNS server will look for service B account 3 example local. It will have no clue about it. So next thing it can do is it can look for the shared resolver rule which is linked with this VPC. So it will check this rule, and this rule will say that you have to go to the outbound endpoint. So it will go there. Its ultimate goal is to reach the inbound endpoint through the outbound endpoint. So first it will go to the outbound endpoint. If you see, the target IP addresses of this rule is the IP addresses of the inbound endpoint. So it will be forwarded to the inbound endpoint. You can't choose these target IPs of the inbound endpoint manually. They are randomly selected, and there will be two IPs created in two different ACs for load balancing and high availability. From the inbound endpoint, it will be sent to the DNS server of the VPC in the hub account. The DNS server will know that okay, this VPC has already been associated with the private hosted zone in account A and account B. Since the request is for service B account 3 example local, it will know that it should be redirected to the hosted zone with the domain account 3 example local, which is the hosted zone in account B. So it will be redirected to the private hosted zone in account B. Since there is an A record with the name service B account 3 example local in the private hosted zone in account B, the query to service B account 3 example local will be resolved to the private IP of service B, that is ECS service in account B. So when I hit that button from service A, through all these steps, the hostname service B account 3 example local will be resolved to the private IP of service B. Let's see that in action. Okay, it is working as expected. Great. Let me shell into the service A container. Let me do apt update. Let me also install curl and DNS utils. Let me resolve this domain service B account 3 example local. That should give us the private IP of service B in account B. Okay, we have got 192.168.2.104. Okay, it is matching with the private IP of service B. Let me run this curl request. Okay, let me run the same curl request with IP. Okay, don't forget to destroy the resources. All the resources are destroyed successfully. Okay, that's it for this demo. We successfully set up a centralized DNS in the hub account and enabled service A to communicate with service B using centralized DNS and a transit gateway. If you found this video useful, and interesting, don't forget to like, share, comment and subscribe. And make sure to hit the bell icon to stay updated with future videos. Thank you for watching.